Hi, today we're going to have a look at a circle theorem, and that theorem is that the angle at the center is twice that of the circumference when subtended by the same arc. Now you might notice here this is rather strange language, and if you're a bit unsure about what it means to begin with, that's completely natural. So the first thing we're going to do is just try and get a grasp of what in fact it's talking about. So whenever we see a theorem or a definition or whatever, we always need to pick out the key words. Okay? So you might remember from GCSE that the circumference of the circle is just the perimeter of it, so the distance around the outside. And then the arc is just a fraction of that. So the arc that we're looking at in this particular case is this guy down here along the bottom. But then we see this rather strange language of these angles being subtended by. What on earth does that mean for them to be subtended by this arc? Well, all that it actually means for an angle to be subtended by a particular geometric feature is that the angle is created by lines that start out at the endpoints of it. So in this case, these angles at the center and at the circumference to be subtended by the same arc, it means that they are created from these lines that come out of these blue endpoints, the endpoints of the arc. To give you another example, just to clear it up, for angles to be subtended by this squiggle, it would mean that they would be created like this from lines that come out of the ends of that squiggle, and that's all that means. Okay, that's all that means. Right then, so how do we now go about proving the theorem? Okay, well, we've got this toolbox over here of key mathematical facts from GCSE, which we're going to need to use. So you'll see actually whenever you're doing circle theorems, triangles, knowing your triangle facts are going to be incredibly useful, especially if you ever spot that your theorem has a center to it. Okay, so when there's a center within your circle, the properties of an isosceles triangle often come into play, and the reason for that is, as you see, that we've got these lines here and here are going to be the same length. Pause the video if you like to think about why that might be. Okay, so they're the same length because they're both a radius of the circle, and so they've got to be the same length as one another. So if we could create another line, then you could have an isosceles triangle. So that's incredibly useful to know. Now, what we want to do is get on to proving this. So immediately I'm thinking, well, can I create some useful triangles that can help me, that involve the angles that we're talking about? So you might have thought, okay, well, why can't I just create this triangle down here? The problem with doing that, and that does create an isosceles like I was talking about, is that it doesn't really involve the other angle, and so it's not particularly useful. So instead, okay, I'm actually going to create triangles like this, because then the other angle is really involved in the diagram, and that is going to be incredibly useful. Now, what you might have noticed is by doing that, I've created a pair of isosceles triangles. Okay, just pause the video if you need a bit of time to see if you can spot those. I've created a pair of isosceles triangles, and because of that, I'm going to have a lot of facts. I'm going to have some facts that I know that I can then apply. Okay. Now, what I want to do straight away is to label my angle at the top, or the angles at the top, and I'm going to label them X and Y. Now, then I can say that the angle at the top is X plus Y. Now you might be wondering why I've used different letters here. Why are they not just both X? Well, it may look a bit like I've split this in two, but not necessarily. We don't know that these angles, that they're the same size and that I've actually perfectly cut this in two. There's no reason why that has to be, so I give them different letters, X and Y. And then I can begin to fill out my diagram. This angle down here is going to have to be X because these are the base angles in the isosceles triangle on the left here. And this angle down here will have to be a Y for the same reason. Okay, and then we can actually keep filling out all the angles in the triangles. Okay, and the more angles you fill out, even if you don't know where you're going with it, the closer you're going to get to having all the information you need. So even if you're a bit unsure about where this is taking you for now, fill out as many angles as you can. And if you notice, the angles that I'm about to fill in, these two angles at the center, they're actually very close to the angle I want to find. So that's a good hint that we're onto the right thing. So now, I'm just going to label what these should be. Can we remember from fact 2 in the toolbox what the angles in a triangle add up to? Okay, pause the video and see if you can then write what that angle should be. Okay, so it should be 180 degrees minus 2 x's. Okay, and this guy over here is going to similarly be 180 degrees. Sorry, that looks like 280 somehow. Let's cross that out and make it clearer. 180 degrees minus 2y. Okay? And what this allows us to do is have so much in the picture that we're actually going to be able to find the final angle that we're interested in, this red angle at the center. Now, which fact in the toolbox can we use? What looks similar in the toolbox to what we've formed here at the center with these triangles? Can you see that it should be fact 1 that we can use? That the angles around a point add up to 360. So the remaining red angle that we want to find is going to be 360 degrees minus 180 degrees minus 2x minus 180 degrees minus 2y. Now it's really, really important that I use these brackets here, because I want to take away each angle each time. Okay, and if I don't do that, okay, if I only take away the 180 or part of it and don't use the brackets, I'll end up with the wrong thing. So you've got to be careful. Now it's just algebra, so I just expand my brackets like so, and what we then get is 360 minus 180 degrees plus 2x minus 180 degrees plus 2y. And hopefully what you can see is that the numbers actually cancel each other out, because 360 minus 180 minus 180 is 0. So you end up with just 2x plus 2y. That expression is what you end up with. Now hopefully you can then see that we've proved the theorem. So I'm going to write QED, because 2x plus 2y is double x plus y. That should be clear for us all to see. And there it is. We've done it. We've managed to prove the theorem. and I think it's pretty neat and pretty tidy. Well, maybe not my handwriting, but the theorem is pretty neat, pretty tidy. So these circle theorems can actually be really satisfying once you get into doing them, once you learn how to prove them. And actually, it's similar ideas each time. So if you found this lesson at all helpful, mention in the comments. If you would like help with other theorems or anything in maths, do please mention that in the comments, and I'll be happy to make other lessons for you. Thanks so much for your time, and take care. Cheers.